Today we're tackling one of those engineering and mechanics problems that looks absolutely terrifying, but is actually super smooth once you get the logic down. Don't worry, I'm not here to drown you in a sea of textbook formulas or heavy theory. We're going to break this down in the simplest, most straightforward way possible. So let's get into it. The problem is asking us for two things. First, the reaction force at point A, which is RA. Second, the deflection at point B, basically how much the beam sags. Now, the absolute cleanest way to save your life in these problems is using singularity functions. We'll start our equation at the very bottom level with the load function, which is Q of x. Let's do a quick refresher on the golden rule here. How do the exponents change when loads enter our equation? For point loads, our exponent is always -1. For rectangular distributed loads, it's 0. And if we had a triangular load, it would be 1, along with its slope coefficient. Looking at our problem, we only have a point load and a rectangular load, so we're chilling. But watch out, here's the big trick. The rectangular load doesn't go all the way across the beam. It stops right at L/3. So to cancel it out in our function, we add an imaginary upward load exactly at the L/3 mark to cancel it out. Just like that. Awesome. Now that we got our Q of x equation, let's move to step 2. We can't just jump straight to the moment, so we gotta take it step by step. We integrate Q of x once to get our shear force, which is V of x. This part is super easy. Just standard integration. Add 1 to the exponent, divide by that number, and done. Don't even worry about what's inside the parentheses, just treat the whole thing as one single block. Don't stop there. We integrate one more time to get the bending moment equation, m of x, which is what we actually need for deflection. All we do is integrate v of x. Quick pro tip here. If there was an external concentrated moment on this beam, this is exactly where we drop it into the equation. It's super simple. You just find where it's applied, put it in the parentheses, raise it to the power of 0, and you're good. But since we don't have one here, we keep moving. Boom. Now we have a beautiful moment equation. If we integrate this bad boy once, we get the slope. Integrate it one more time, and we get the actual deflection. You can see the integrated versions on the screen right now. But hold up, we ran into a little problem. C1 and C2 are integration constants. We can't solve for deflection without finding them first. So who comes to the rescue? Boundary conditions, obviously. Let's look at the supports. At x equals 0, the support keeps the beam from sagging, so deflection is 0, meaning yi equals 0. At the very end of the beam, at x equals L, we have a fixed support. What does a fixed support mean? No sagging and no rotating. So at x equals L, both deflection, y is 0, and the slope, theta is 0. Plugging these boundary conditions into the equation completely solves C1 and C2. And just like that, the reaction force at A, RA, pops out clear as day. Time for the final blow. The problem wanted the deflection at point B. Where is point B? At the L/3 position. All we gotta do is substitute L/3 everywhere we see an X. And honestly, here is the most beautiful thing about singularity functions. If the inside of the parentheses turns out to be 0 or negative, you straight up throw that term in the trash. It just becomes 0. This shrinks our massive equation down instantly, and we get the deflection at point B smooth as butter. And that is how you crush this problem cleanly and simply. If you're loving the series where we skip the boring textbook fluff, make sure to hit that subscribe button and drop a like. In the next video, we're going to break down triangular loads and how external moments affect the system. Take care of yourselves, guys. Catch you in the next one.